Alright, so we're going to finish up section 6.1, and then we'll see what kind of time we have if we start 6.2. We start it today or tomorrow, and we're going to stop at 6.2 part 1. Alright, so first thing we're going to talk about in this section is arc length. So remember, an arc is just part of a circumference. So we're talking about arc length. We're talking about finding the length of part of the perimeter of a circle. Now, one thing we want to talk a little bit about is how the length of an arc connects to the size of the angle that makes the arc. All right, so let's take a look at this. Here's a circle. And let me draw in an angle. I'm going to make that a 90-degree angle. And there's the arc that's connected with that angle. So the arc is where you look at the two rays that come out from the center, look at where they hit the edge of the circle, and then connect those 2 points where they hit. Okay, so what size is that angle?
90.
That's a 90-degree angle. And when you draw a 90-degree angle, what's the size of the arc, say, compared to the whole circle?
Is it a unit circle?
It could be any circle.
It's going to be 1/4 of the circumference.
Yeah, so a 90-degree angle basically gives you an arc that is 1/4 of the circle. All right, now let's draw a picture again. And this time I'm going to double the size of the angle. And I want to look at what happens to the size of the arc. Okay, so draw my circle. Again, any size circle. There's my initial side. There's my terminal side. There's the 2 points where the sides of the angle intercept the circumference. And there's your arc. Okay. How big of an angle did I draw this time? Yeah, that's a 180-degree angle. And if you draw an angle that's 180 degrees, what's the size of the arc that you get? Yeah, so in this case you get an arc that is 1/2 of the circle. So now let's look at what we did to the angle, and then let's look at what happened to the arc. I went from 90 to 180. What did I do to the size of the angle?
Doubled it.
I doubled it. The arc went from taking up 1/4 to taking up 1/2. What happened to the size of the arc? It what?
It doubled as well.
It doubled as well. So what that means is arc size and angle size are directly proportional. If you triple the size of the arc, you will triple the size of the angle. Right? If you make the angle half as big, you make the arc half as big. Okay? They are directly proportional to each other. Any question on that idea? It doesn't matter on the size of the circle. It's the same for any circle. All right, so directly proportional. So what that means is we are going to be able to set up a proportion to figure out a formula for arc length. And the only reason we can use a proportion is because they are directly proportional. If they weren't, you couldn't. And the idea that we're going to do is very similar to something I mentioned yesterday. Anytime that you want to figure out a formula for something, you just need one fact about that to start with. So let's say you wanted to come up with a formula that converted feet to inches. What would be a fact that's true that connects feet to inches? Yeah?
12 inches is 1 foot.
Okay, 12 inches. There is 1 foot. So that's a true fact that I'm starting with. How did we know that fact? Well, that's something you'd have to look up or have memorized beforehand. So you've got to start with something that's true. Now, is that true? Yeah, I could start with that. It doesn't matter what I start with. I just have to start with something true, preferably start with something simple. Okay? Simple means it usually has a 1. And then let's say you had 94 inches. And you want to know how many feet that is. There you go. You set up a proportion. Okay. And if you set it up with the 24 and the 2, you'd get exactly the same answer as with the 12 and the 1. So any question on that idea of just starting with something that's true? Anything? Okay. So now we've got to figure out something that would be true in this diagram. Right? So we're going to focus on 4 of the variables here. We have an arc and an angle that creates that arc. And we have another angle and another arc. And those 4 things that I circled are going to allow us to set up a proportion. But we have to figure out something that would be true. Right? And I'm going to give you a hint. Suppose that theta 1 was 1 radian. This angle right here. Pretend that that was 1 radian. That tells you something else. This was the first thing I mentioned to you about radians yesterday. Before I even gave you a formula, I gave you kind of a visual. And I said that if this angle is 1 radian, something special happens. Does anybody remember what happened if this angle was 1 radian? Yeah?
I'm pretty sure the other one's like 1, whatever kind of measurement is being used.
So on a unit circle, yes, the arc and the angle were the same. But I'm thinking of something else that's here. Something to do with this R. Yep.
You're saying the radius is the same
The radius is the same as what?
as the radian?
Nope. That's not the same. Yep.
The radius should be the same length as the arc.
Yes. If you make this angle 1 radian, then it automatically makes the arc the same size as the radius. This fact is going to be like our 1 foot, 12 inches. It's a starting point that we know is true based on a definition. If you draw an angle that is 1 radian, by definition, the size of the arc that is created matches the radius of the circle. That's a true fact. So we're gonna use that. Okay, so this part right here, that's like my 1 foot is 12 inches. It's a starting point. Now, I don't have to use 1 radian and radius, just like I don't have to use 1 foot and 12 inches. I could use 2 feet and 24 inches. But I'm trying to use the simplest fact I can think of that I know is true. So now let's set up a proportion. Can somebody set up a proportion for me using the 4 things that are circled? Yep. Just
theta
these
1.
4. Yep.
Oh, well, I was going to say theta 1 over S1
Okay.
equals 1 over R. But I guess theta 1 over S1 equals theta over S.
Yes. You can set that proportion up lots of different ways, as long as you're consistent. If you put theta on the top on the left, just make sure you put it on the top on the right. The important thing is the diagonals. Theta 1 and S should be on the same diagonal, and so should S1 and theta. Now, we have a proportion. We have to fill in one side of the proportion with a true fact. Okay, so that's what we're going to fill in, which I think you started to do. So can you tell me, if you fill in what we have as our fact, what would it look like?
That 1 over R equals theta over S.
So 1 over R, because that's our 1 foot 12 inch idea.
Equals theta over S.
Yeah, and the other side, we just leave it like that. That's where we would plug things in from the problem. All right. Now, I want to solve that proportion and get S by itself. Okay, how do we solve a proportion?
Just cross multiply.
And what do you, so when you cross multiply, what do you do?
So it would be, well, one answer is S equals R times theta.
Yep, exactly. 1S equals R times theta. And that's the formula for the length of an arc on a circle. S is the arc length. R is the radius. And theta is your angle. But we got to be careful with it. Because if we go back up, what did we assume about our angle when we started this whole process?
That it was like 1 radian.
Right. The fact that we based the formula on was that 1 radian makes the radius the same as the arc. 1 radian. We didn't say 360 degrees, or we didn't use anything in degrees. We said 1 radian. So that means in this formula, when you plug an angle in, what do you think the angle has to be in?
Radian.
Has to be in radians. Now, if you don't want it in radians, you could adjust the formula, and you could put in a 180 over pi, which is the conversion. So you could put the conversion into the formula. But then it starts to get a little more messy. So it's a very, very clean-looking formula if you do it in radians. S equals R theta. Okay, and the idea is I will give you 2 out of 3 of those variables. You plug them in, and you'll find the third one. Make sure you put a label. S is a length. R is also a length. Theta is an angle. Okay, so whatever you're solving for, make sure you put the appropriate unit. All right, let's try this one. So find the length of the arc. If we have a circle with a radius of 2 and an angle of pi over 4. So what they might do in a problem is just give you the sentence like that. It might give you a diagram to go with it, or it might give you both. Okay, so we got a radius of 2, an angle of pi over 4,
What's your
Bless you. And the goal is to find the length of the red arc. Okay, first thing to determine is the formula you're going to use. Okay, what's the formula that we use to find the length of an arc? Yeah.
X or S equals R theta.
Yep, S equals R theta. And now we're going to fill in everything we can. Well, the question says find the length of the arc. So what letter are we going to be solving for? We're solving for S. Well, if that's what you're solving for, then they better have given you everything else. What's the radius? 2. Be careful if they tell you like the diameter of the circle and not the radius. If they give you a diameter, how do you convert it to a radius?
You get divided by 2.
Right, you take half of that. Yeah. Okay, but they gave us the radius. It's very clear that the radius is 2. That is not a diameter. Okay. And what about my angle? Yeah. Pi over 4. What's the unit on that? It's in radians. How do you know? Well, I could write a fraction with pi in it and still have it be degrees. It'd be strange, but I could. How do we know that that's radians, though? Yep.
There's no degree sign.
Right, the absence of the degree symbol. Okay, you could technically do something like this. And that means pi divided by 2 degrees. But if you don't put a degree symbol, that's when you know it's radians. Okay, so it's already in the unit that we want. What's 2 times pi over 4?
2 pi over 4.
2 pi over 4, which reduces to
pi over 2.
pi over 2. Okay, and what did we just find? Arc length. That is a length. So you need a label on that that represents length.
Is it inches?
In this problem, it is inches. Yeah. That's it. So that's the length of that arc. If you wanted it as a decimal, it's about 1.57 inches.
On the test, if it doesn't specifically ask for radians, are we allowed to put in it has like pi in the answer? Are we allowed to do the whole thing out and then have like 3 decimal places with the final answer?
I would say your option you should always do is leave it as an exact fraction.
For the
Only
final
do the
test.
decimal if they ask for it.
For the tests.
Everything.
Okay.
Yep. Homework, tests. When you're at a restaurant, the waiter asks you all the time.
Got it.
Just leave it as a fraction. The only time you want to do a decimal is if they specifically tell you.
Got it.
Yes.
So when you got the 2 pi over 2, did you do it like by just simplifying, by basically saying like the 2 times the pi over 4 was just 2 over 1?
So the 2 times pi over 4 was 2 pi over 4, and then we just reduced it. Yeah. If it was like 3 times pi over 4, then we would have just left it as 3 pi over 4. Okay, but always reduce it as much as you can. Okay, so that was finding the arc length. Let's try, I think this one is still arc length. Nope. It's radius. So now we're going to find the radius of this circle, and they're going to tell us the other 2 things. So the arc length is 3 pi, and the central angle is 60 degrees. Okay, before I even write down the formula I'm going to use, is there anything that you notice in that information that's given that we're going to have to change to make it work with our formula? Yep.
60 degrees to radians.
Right, we've got to change 60 degrees to radians. And that's what we talked about how to do yesterday. What is 60 degrees in radians? Yep.
Is it pi over 3?
Yeah, pi over 3, very good. Okay, so we convert degrees to radians. And now we're ready to use the formula. What's the formula that we use again for arc length? Xavier?
S equals R theta.
S equals r theta. Okay, fill in everything we know. Do we know S in this problem?
Yes.
Yeah, what's S going to be?
3 pi.
3 pi. Do we know R?
We don't know the arc length.
We don't know the what?
Arc length.
That's what you just told me.
I mean the radius. We don't know the radius.
We don't know the radius. We're going to leave that as R.
Pi over
And-
3 for the angle.
Pi over 3 for the angle. Okay, now we want to get rid of, we can get rid of the pi and the 3 at the same time. What would you do on each side to get rid of the pi and the 3 at the same time? Yeah?
Could you multiply by 3 over 5?
Yep, multiply each side by the reciprocal. So now pi's cancel, 3's cancel, pi's cancel, and we're left with a radius of 9 feet. Okay, 9 feet. Any question on that? Okay, so that's an example where you found the radius. We did one where you found the arc length. Let's do one where you find the angle. Okay, since I'm not planning on getting to the second part that I normally would. We have a lot of extra time. So let's do 6C. 6C. All right, so find the angle. I'm not going to write out the whole sentence. I'm just going to give you the information. So the radius is 2 inches, and the arc length is 4 pi inches. Well, first of all, make sure the radius and the arc length are the same unit. If one of them's inches and one of them's feet, well, that's going to mess you up. So you got to make sure you have all the same unit first. We do, so we're fine. Let's go right to our formula. What do they tell me the arc length is this time? How much? 4 pi inches. Okay. What do they tell me the radius is? Yep. 2 inches. And the angle? I don't know. Okay, so solve to get theta by itself. And what's my angle this time?
Two pi equals theta
2 pi what?
equals theta.
Well, 2 pi, I'm looking for
Inches.
Nope, not inches.
I mean, two pi radians.
Radians. So do I need to write anything down after the 2
No.
pi? No.
Because the way you tell difference is in the degrees or lack of the degree symbol.
Right. So you don't put anything if it's in radians. You just write the number. Now, what if they said, find the angle, write your answer in degrees? What if they did one? What's 2 pi the same as?
Then you can multiply it by pi over 180.
360. Yep. So this would be equivalent to 360 degrees. You'd multiply, did you say 180 over pi?
No, almost what? Oh,
It would be 180 over pi.
I said pi over 180. Sorry.
Yeah. Okay. So any question on the arc length formula? Finding the arc length, the radius, or the angle? Okay. So then, next thing we're going to look at is what's called angular velocity. So angular velocity basically measures the speed of something that's spinning. Right? For example, if some power tools are measured in like how many revolutions per minute they make. Okay, one of them I can think of is like a Dremel. It's like a drill kind of, but it spins faster. It's a little different. So that may have a speed of like 10.
Are normally used for like finishing work.
Yeah.
And stuff. They're also called rotary tools.
So yeah, it's like it spins at maybe 10,000 RPMs. They don't measure it in like miles per hour. Okay, same thing with like your car. If you look at like the engine speed, not the speed the car is moving at, but like the RPMs, right? It measures the engine speed. Well, it's measured in RPMs, revolutions per minute. So that's an example of an angular velocity. Okay, it measures the speed of something spinning. We have 3 different ways that we can measure something spinning right now. We can use degrees to describe how much rotation we've had. We can use radians, or we could also use revolutions. Those are the 3 units we've talked about. The default measure that you always use, okay, in like this class, if they do not tell you what to use for the speed of something spinning, is radians. The time unit can be anything. Okay, it could be radians per second, radians per minute, radians per hour. Time unit, that can change. But the default spinning unit is radians. Not as common to use radians, like in real life, it's more revolutions. Okay, but we use radians. Right, and that's called angular velocity. You measure the speed of something spinning, or you can also call it angular speed. Same idea. So the question is, why do you need another type of unit to measure speed? Why don't we just stick with the unit we always use, like something that's linear, like miles per hour, kilometers per hour, feet per second? Why don't we just use that? Well, let me show you something. Does anyone remember the formula for distance? Distance equals, it's like 2 letters. Rate times time. Okay. Distance equals rate times time. So let's focus on those 3 dots. And what I'm going to do is I'm just going to spin it 1 time. So I'm going to spin it so the green handle up there goes all the way around and then comes back up. So So as I spin it, okay, so watch kind of what's happening to the dots. Okay, they all just made one revolution. But which dot traveled the farthest?
The one on the very outside.
Yeah, this, the one on the outside, that one traveled the farthest. And then which one traveled the least?
The one in the center.
Yeah, the one in the center. If it was exactly in the center, it wouldn't have moved at all. But they all traveled whatever distance they traveled in the same time. Okay, whatever distance they traveled, they all did it in, let's say it took me 2 seconds to bring that all the way around. So they traveled different distances, but they did it in the same time. So what would that have to mean about each of these dots? They traveled different distances in the same time. That can only mean one thing. Yeah?
Different rates.
Right, they have different speeds. So technically that would mean the outer dot was going the fastest. Then the red dot was kind of in the middle. And then the black dot, well, maybe that had 0 speed. Didn't move at all. Right? So when something's spinning, if you try to think about it this way, this is thinking about it in a linear way. It gets too confusing. So what we do is we describe it as how many revolutions did the dots make. And they all made one revolution in 2 seconds. So each one of these dots has the same angular speed. They all have different linear speeds. But that's why we use angular speed. It simplifies the idea of something spinning and describing how fast it's spinning. Any question on that idea? Okay. So angular speed, I said it earlier, is always measured in radians per, and then you have a time unit. Now, if they tell you in the problem to use a different unit than radians, fine. If they say find the angular speed in revolutions, you can do it. But if they don't give you a unit, I want you to use radians. On a test, I would be clear and I would always tell you the unit. But there's going to be some problems in the homework that say find the angular speed, and they're not going to tell you anything. I want you to use radians. Yeah.
What exactly would radians per, let's say, for time seconds would look like?
Wait, what the answer would look like?
No, like, how would it look like, if you were to give an example? Because revolution is like...
Radians is the same thing. Degrees is the same thing. It's like just different ways of saying the same thing. It's like if I said, how many feet from here to the wall, how many inches from here to the wall, how many centimeters. It's all the same idea. You're just measuring in a straight line from point A to point B. You're just using different units to do it. So they're all spinning in a circle. We're just using different units to describe the spinning. Now, the difference between the two speeds, linear speed, that's used to measure something moving in a straight line. Miles per hour is probably what you're most familiar with, but you could have kilometers per hour, feet per second. Anything that measures distance in a straight line, per, and then a time unit. So what we're going to practice doing first is just converting like a simple unit, like say seconds to days. Okay? Then we're going to practice converting a rate. Okay? A rate has two parts to it. It not only has a time part, but it also has a distance part. So we'll practice converting all of it. Okay? And the way we're going to do it is we're going to look at our units and look at our dimensions. And we're going to kind of analyze our fraction, and we're going to make units cancel out that we don't want. So to make things cancel out, we need conversion factors. So some conversion factors that I would expect you to know, take like for a test, how many inches in a foot, how many feet in a yard, how many feet in a mile, how many seconds in a minute, how many minutes in an hour, hours in a day, days in a year, standard year. That's pretty much it. I wouldn't ask you to know something like how many millimeters in a mile. Who knows that? Right, it's kind of a weird conversion. But all the ones that I just said would be ones you need to know. Are there any conversions I just mentioned that anyone isn't sure? Yep. Feet in mile. How many feet in a mile?
It's like
5,280.
How many?
5,280.
5,280. Yep. You gotta love our system of measurement. It's a great one.
No. It's just from the notes.
5,280. Metric, everything's a lot simpler. It's all based on 10. Right, so.
Feet in a yard, please.
How many feet in a yard?
Yes.
Anyone? Yep. 3. 3 feet in a yard. Why 3? All right. So let's try some conversions. Okay. The first one is just a straight conversion. It's not a rate. It's just a time. So 3 days to minutes. So what I like to do is whatever I'm converting, I always make sure it's a fraction. And I'm going to convert 1 unit at a time. Okay, I'm not going to jump right from days to minutes because I don't know how many minutes in a day off the top of my head. I'm going to go from days to the next unit down. Okay, so what's the next unit down from a day that's smaller? Yep.
Hours.
Hours. So we're going to first get days to hours. Okay. I want days to cancel out. So where is days going to go in the second fraction? It's going to go in the bottom. So we're going to have days in the bottom, and we're going to have converting days to hours. We're going to have hours in the top. Now I need the conversion. What's the connection between hours and a day? Yeah.
24 hours in a day.
It's 24 hours in 1 day. And now, if you did that calculation out, you'd be left with hours. All right, let's go down again. The next unit down from an hour is a minute. Even if you don't know the conversion between minutes and hours, you should know where the unit is going to go. Where's hours going to go? Top or bottom? It's going to go in the bottom. And then what unit would go in the top? Minutes. And now you just have to fill in your conversion. How many minutes to how many hours? You can technically fill in anything you know that's true. It's better to use something simple. Yep. Great. Or 60 minutes in 1 hour. Okay, and when you're done, you just multiply straight across. Sometimes the denominator is all ones. It depends. In this case, it is. And we just do 3 times 24 times 60. So 3 times 24 times 60. Okay, so there are 4,320 minutes in 3 days. So any question on converting from days to minutes? So that problem just dealt, the final answer just had a single label. Okay, now we're going to look at something that has 2. I'm starting with feet per second, and I want to convert that to miles per hour. So I need to do a conversion with a distance and another conversion with the time. Now, feet per second. What kind of speed would that be? Is that angular or linear? Yeah.
Linear.
Linear. And then miles per hour. Is that angular or linear?
Linear.
That's still linear. So it's a little bit more complicated because we got to deal with 2 different units. But it's still linear to linear. Okay, we're not doing angular to linear yet. Okay, still linear to linear. So you're traveling 50 feet. And what does that really mean?
Feet per 1 second.
Per 1 second. That's 50 feet per 1 second. Okay, so we got to convert two different units. Do we want to deal with the length unit first or the time unit? Which one?
Time.
Time, okay? So we need to get seconds to hours. Okay, so let's start with that. We want seconds to cancel out. Okay, so where's seconds going to go? It's going to go in the top. And we're trying to get to hours. So what's the next unit up from a second?
Minute.
That's a minute. And what's the connection between seconds and minutes?
61.
So 60 seconds, 1 minute. If you stopped here, you'd have a speed of feet per minute. Go ahead, let's keep going. Now we want to get rid of minutes. Okay, so where does minutes go? Yeah.
Put minutes on the top and then hours on the bottom.
And the conversion between minutes and hours. Yeah.
60 minutes.
So we get 60 minutes in 1 hour. Okay, so if you stop there, you now have feet per hour. So you have the time unit. Now you need the distance unit. Okay. We want feet to disappear. Okay. So where's feet gonna go? Feet's gonna go in the bottom. Okay. What unit is gonna go in the top? Yeah, miles. And now I need the connection between feet and miles. There are 5,280 feet in 1 mile. Feet in the top, feet in the bottom. Okay, look it over, make sure you get the right units. Miles in the top, hours in the bottom. Okay, so let's multiply all that out. So you're going to have 50 times 60 times 60. Well, we can save that one part of it. What's 60 times 60?
3600.
So 3,600 times 50. So there's your numerator. And then divide by 5,280. So this time it's not all ones in the bottom. Okay, so it's 34.09 miles per hour. And so it's a common unit, so sometimes you see that abbreviated with 3 letters, mph. Or you can use the label like I did, miles per hour. The only units I can think of that are, well, the only rates that have 3 letters that I can think of, you got like mph, miles per hour, kph, kilometers per hour, and then RPMs, revolutions per minute. Pretty much every other unit, well, I guess FPS, feet per second, I don't know if that might be used somewhere. I know FPS on like a computer, they use it for
Frames per second.
Yeah, frames per second. So then it could be confusion.
And then there's also dot per inch.
Yeah, like DPI. So I would just stick with writing it like that so we don't get confused with 3-letter abbreviations. Okay. Any questions on that? All right, so that was a linear to a linear. Okay, now, let's try an angular to an angular. Okay, still not going between angular and linear yet. That's going to be the last one. So this is a speed of 200 radians per second. All right, so we got to fix the distance unit, and we got to fix the time unit. Okay, hopefully by now you're getting the idea of the time unit. So there's your time unit. Now we got to fix radians. Again, even if you don't know the conversion, you should know where radians is going to go. Is it going to go in the top or the bottom? It goes in the bottom. So we're going to have radians in the bottom. What unit in the top? Revolutions. Now we need the connection between radians and revolutions. What's the connection between the two? Yeah.
1 revolution and 2 radians.
Yep. 1 revolution and 2 pi radians. So let's multiply that out. So we got 200 times 60, that's 12,000. And then you're going to divide by 2 pi. That's wrong. I looked at that quick, took me about a second and realized that's not right. What did I do wrong? Let's see. Yeah? Yeah, you need the 2 pi in parentheses. There's no way if I divide 12,000 by 6.28, I'm going to get 18,000. So the calculator took 12,000 divided by 2, got 6,000, and then did 6,000 times 3.14. And that's how it got 18,000. Didn't follow order of operations. So I'm going to go back, type in 12,000 divided by, well, it did follow order of operations. It did multiplication and division left to right. But I wanted to do the 2 pi first. And that's what I want. So 1,909.86. Okay, and what's my unit on that?
Revolutions per minute.
That's revolutions per minute. Okay, so any questions on converting angular to angular? All right. So now, let's try this one. So we have a wheel with a radius of 18 inches spinning at 1,850 RPMs is revolutions per minute. So you should know that. RPM is revolutions per minute. That's what it stands for. Okay, so the first thing they want us to do is find the angular speed in radians per second. Okay, that part is very straightforward. It's what we basically just did. We converted a speed from radians per second to revolutions per minute. We're just doing it in reverse. We're going to take revolutions per minute and go to radians per second. And then part B is going to be to convert the angular speed to a linear speed. But remember what we said about something spinning. The further out that the dot is from the center as it spins, the faster it's going as a linear speed. So I have to specify what part of the wheel do you want to know the linear speed for. If it's the linear speed for the center, well, it's 0. Staying perfectly still. But if it's the linear speed of a point on the circumference, that's not going to be 0. Okay, so we're going to have to figure out what that is. There's no real direct connection between parts A and B. You could do part B or A first. You don't need one to do the other. That's what I'm saying. All right, let's do A first. So we have 1,850 revolutions per minute. Okay, what would I multiply by to convert revolutions to radians? Yeah. So 2 pi what? 2 pi radians over 1 revolution. Okay. So now I got what they want for the angular measurement. Now we need the time measurement. How are we going to get rid of minutes? Yeah.
60 seconds on top.
Oops, crossed out the wrong. You said 60 seconds on the top?
Yeah.
Okay. So then 1 minute would be in the bottom?
Yes. Actually, yeah, you reversed.
Now you have a speed of radian seconds per minute squared.
Yeah.
I'm not sure what that means.
Yeah.
So we want to have
60
1
seconds
minute.
on the bottom and
Yes.
on the top.
60 seconds on the bottom, 1 minute on the top. Now, minutes cancels out, and you have radians per second. Right, and we could actually, we could reduce if we wanted to. 2 goes into itself once. That doesn't really do much for me. All right, so let's type that. So we got 1850 times pi. And this is a lot of times why I hit enter and then I do the denominator separate. Then I can avoid that issue if there were 2 things in the denominator of having to put parentheses. So there's your numerator. And then I just do divide by 30. So it's 193.73. Okay, and that is, what's my unit on that one?
Radians per second.
Radians per second. Okay, so that's part A. Now part B says to find the linear speed. Well, you're given angular, you're trying to go to linear. The way that you go from angular to linear is through revolutions. So you want to have the speed back in revolutions. That's why I'm going to go back to what they gave me. So part A, we don't need for part B. And so 1,850 revolutions per minute. Well, in part B, they want to get seconds. So let's deal with that first. What am I going to multiply by here to get seconds?
1 minute over 60 seconds.
1 minute over 60 seconds. Okay, so now we got revolutions per second. But we want to get feet per second. All right, so now I want revolutions to disappear. So how am I going to make revolutions disappear? Where does it have to go?
I'm thinking you need revolutions on the bottom and radians on the top. And I'm thinking that 1 revolution would be 2 pi radians because, like, looking at the circles, like 360 degrees is 2 pi.
So if they wanted you to convert up in part A, if they wanted you to convert like radians per second, that's what we did in part A. So we're not converting to radians in this part. What are we trying to convert to?
Circumference. Arc length?
Well, I'm thinking of a unit. Yeah? Feet. So we're trying to get feet. So we need revolutions in the bottom, and it cancels out. Now, we have to figure out this conversion factor. That's not a conversion factor like how many seconds in a minute, how many minutes in an hour, hours in a day. Those conversion factors are constants. They never change. Why is this conversion factor not a constant?
Doesn't it depend on the radius of like
Right. How many feet in a revolution? Revolution of what? Revolution of this pen or a revolution of the earth? Like, what are we talking about? So the feet in revolution is a conversion that you got to figure out every time. So what haven't we used yet in this problem that's going to help us figure out how many feet in a revolution?
The radius.
The radius. Now, we got to be careful because the radius is in what unit right now? That's inches. How many feet is that? Yeah?
1.5.
Yeah, that's 1.5 feet. So you divide that by 12. So we're going to try to figure out how many feet in a revolution. Well, what's another name for a revolution if you think about it on a circle?
Circumference.
It's the circumference. So what we have to figure out is how many feet in the circumference of the circle. All right, so let's do it. What's the formula for circumference? Yeah.
It's like the 2 times radius.
Circumference equals, so what circumference equals 2r?
Yeah. No, it doesn't. It's something else.
Yeah, circumference isn't just double the radius. You're kind of close though. Yeah? 2 pi r. So circumference equals 2 pi r. Our radius is 1.5. So what, just in terms of pi, what is the circumference of my circle?
3 pi.
3 pi. Now I know there are 3 pi feet
In one revolution.
in one revolution or one circumference. That is what makes the conversion between angular and linear, that step right there. So now you're left with feet per second. Right? So that's the only tricky thing about converting angular to linear. You need to use the circumference formula.
Could you scroll that up to the circumference formula that we just did?
Yep, circumference equals 2 pi r.
Oh, okay.
And now we'll multiply straight across. Okay, so we got 1850 times 1 times 3 pi. And I'm going to divide that by 60. So that's a speed of 290.6 feet per second. So the way you can kind of visualize that is imagine you had like a tire on a machine, okay, spinning at 1,850 RPMs. And all of a sudden the tire fell off the machine, it hit the ground. It didn't lose any traction. And all the energy that it had spinning went into shooting it in a straight line. That's how fast it would be going if it hit the ground. 290 feet per second.
Like that's really fast, what you're saying?
Yeah, that's pretty fast. If you look back at this problem we did, just as an idea, 50 feet per second was 34 miles an hour. This is almost 300 feet per second, so it's almost 6 times as fast as this problem. So that's close to 200 miles an hour. You're probably not getting out of the way, unless you're a long way away from it. Now, okay, so any question on that? Okay, so that's the second part of 6.1. So tomorrow we will do 6.2 part 1. Okay, so same page, same section as last night. So when you open the PDF, make sure it says page 324 at the bottom. And it's 56 to 61 and 70 to 73.